Hello everybody and welcome to Computer Science 1002, Introduction to Logic for Computer Scientists. You may be wondering why would you start your computer science degree with logic of all things. This is similar to how you would start physics with learning calculus. Logic is everywhere in the systems that make decisions, and pretty much every computer system you could think about would be making decisions. A self-driving car needs to be making decisions. People who write software for your laptop build decisions for that software to make. But not only logic is used to be making decisions in computer science, the very description of those systems is written in the language of logic. The circuits, the hardware circuits on which those systems are build on logic. And in order to get things like banking and internet to work, we also need logic to prove that your banking is secure, to prove that when you're watching a video, you will actually get all the frames of the video you are watching and not something completely different. But before we can teach systems to think logically, let's see if this comes natural to us. Do we ourselves really think logically, or is thinking logically a skill that we need to pick up? Let's try a little puzzle. You see the following cards. Every card has a letter on one side, on the blue side, and a number on the other side, on the green side. So every card is blue and a letter on one side, and green and a number on the other. Now, what card do you need to turn out of the 4 in front of you to check that it is true that if a card has a J on it, then it has 5 on the other side? Just the 4 cards in front of you. You are trying to see if all the cards in front of you with a J on one side have a 5 on the other. So think about it for a second and try to see which cards you absolutely need to turn and which cards will not give you any new information if you turn them. So first you probably went to the card with a J and said, if I need to check that every card with a J has a 5 on the other side, then I better flip over the card with a J. So you flipped over that card, found that it does have a 5, and you say, yeah, so far so good. So far it seems that every card with a J has a 5 on the other side. Now, is there any other card which you might need to flip, which may tell you that actually no, maybe not every card with a J has a 5. So what happens if you turn the card on which you see a 5? Sounds reasonable because you're talking about cards with a 5 and a J. Suppose you turn it over and you see a C. Well, does it really tell you anything about cards with J having 5 on the other side? Not really, because if it were a J, you'd be happy, and if it is not a J, you're still happy. So turning the card cannot really change your opinion whether every card with a J has a 5. Do you need to turn a card with a B? Well, probably not for the same reason. It's not a card with a J, and you don't care about cards without the J. But let's look at a card that has a 2 on it visible. What if you turn it over and see a J? Now, wait a moment, you got a card that has a J on one side, but on the other side there was a 2. Now you say, wait a moment, that was wrong. Not every card with a J has a 5 on the other side because I just found a card with a J and a 2. So with this, you would have disproven that every card with a J has a 5 on the other side. You could try think about it or asking your friends and relatives, and you'll see how many people would think that you need to turn the card with a 5, but would not think of turning the card with a 2. So if you're wondering what is the actual answer, what kind of answer should be there in general, you would need to turn every card on which you see a J, and you also need to turn every card on which you see a number other than 5. Turn card with a 5 doesn't tell you anything new. Turning a card with something not a 5, like a 2, can reveal a J that you think shouldn't be there. So this is the first example of a sentence with a logical structure. In this particular case, the logical structure is if you have some event, something that we will call A happening, then another event that we will call B would be happening. For example, if we have a card with a J on it, then the other side of it should be 5. So let's just see what circumstances make it true so that you could see what kind of scenarios you need to check to verify that statement. So first of all, if there is a card and you see a J on it and there is a 5 on the other side, that's totally fine. In this case, having a J on one side is true, having the 5 on the other side is true, and indeed the statement, if it has a J, then it has a 5 holds for that card. Now, what if you have a card with a J on one side and a 2 on the other side? Well, now there is a problem because you were saying that a card with a J must have a 5, but you found a 2. So in this case, you said, no, my assumption that everything with a J has a 5 was not true, and I've disproven my hypothesis. But what happens if your assumption is false? For example, you have a card with a B on it, not a J. Then it really doesn't matter whether it has a 5 or 2 on the other side, because you're really not interested in cards with with B. You're only interested in cards with J. So in this case, your statement, every card with a J has a 5, would still be true, no matter what you can find on the other side of the cards with a B on them. So a lot of time when you see people thinking, so to say, logically, they may be thinking that if-then statement goes both ways. But as you could see in this example, it usually doesn't. So here are a couple of examples to get you thinking about if-then statement going only one way. Suppose you live in Newfoundland. Then you must pay the HST tax. Oh well. You might conclude from that that the only way you would pay HST tax is if you live in Newfoundland. But suppose somebody lives in British Columbia. You know what? It could be that they also have to pay HST, or it could be that they're spared. Either way, it will tell you nothing about whether if you live in Newfoundland you must pay the tax is true or not. Or think about a politician who is running on a promise, if I'm elected, then I will build a regional transit system. What would be a situation when you could hold her accountable and say, wait a moment, you didn't deliver on your promise? Well, if she is elected and does not build a regional transit system, then she did not fulfill her promise. But then if she is not elected, she may still go and try to campaign for regional transit system. Whether she succeeds or not, it will have nothing to do with her promise, because her promise only referred to her being elected. One reason we will want to translate things into logical language in this course is because natural language tends to be really ambiguous. Sometimes people derive things from the context which are not really there, and different people would say the same thing and would mean something different. So here is one example where natural language, such as English, gives completely different meaning to the same very, very common word, completely different meaning from the point of view of logic. Suppose I say, can I have a piece of that pie? Any piece. You would interpret my words as, okay, here is one piece, and it doesn't matter which one from the pie, here. On the other hand, if I say, any student in my class can reason logically, any student knows this. What I mean is every one of you knows this. I don't mean just give me one student who does. So here is another example with the same word. If I say any student can get an A in this course, by any, I mean every single one of you can get an A in this course. If I say, well, would any student get an A in this course? That question is more about, is there at least one student who will get an A? Before we finish this lecture, as we will do in many other lectures in this course, let me give you a puzzle to ponder before you watch the next video. Suppose you see two identical twin brothers, Dave and Jim. And one of those brothers always lies. Everything he says is a lie. Another brother always tells the truth. If he says something, it must be true. Now, suppose you run into one of them on the street and you're trying not to be impolite and figure out, are you talking to Dave or are you talking to Jim? What is one question, a single question with a yes-no answer that you could ask the brothers that you met to figure out their name? It's important to know that you only care about their name. You don't know which one of them is a liar, nor do you care to know at this point. So I'll let you think about it. What kind of question you could ask the brother you met to figure out what is his name?